Swayam Prabha. Digital India. Educated India.
So, in the previous class, I was discussing PIV technique. So, PIV is particle image velocimetry technique, which is used to measure velocity of fluids, okay, which is a planar technique. And then we have seen the issues when we apply PIV to multiphase flows to measure dispersed phase. Still we can measure particle velocity, but considering that in your interrogation window you now have particles of different size. So what you get is some kind of average particle size, averaged particle velocity that may not correspond to any particular size. In fact, it will be biased towards larger particles because they occupy more space in your interrogation window. And this is based on cross-correlation cross-correlating the images at two different time intervals, okay, which are captured at two different time instants, with short time interval. Then, now to measure the continuous phase, we need to put seeding particles in the flow. So now in your PIV images, you have dispersed particles as well as seeding particles. But direct application of PIV again won't be meaningful because the velocity you will be getting, you don't know if that corresponds to particle phase or carrier phase. This means that we have to separate the two phases. And there comes the leaf-based PIV techniques. So in that case, we add some dye to either to tracer particles or to the dispersed particles, and using appropriate light source, using appropriate filters, we can separate the phases while acquisition of the images. While we are acquiring the images, at that time itself, we can separate the phase. But still it is possible that for one of the cases you see both particles as well as tracer particles, but considering that you would have acquired either the particles or the tracer particles uniquely, you can separate the two phases. Okay. So, but still with this approach, some amount of crosstalk is possible. However, this technique works well if we have dilute loading. But the major limitation of this approach is that we don't know what is the particle size. So if we have broad size distribution of particles, for example in sprays, then measurement of only particle velocity is insufficient. We must know what is the particle size. So now the question is, how can we achieve this? So for that purpose, we need to rely on a planar technique for measurement of particle size, and that's what we'll discuss now. So now we'll discuss about interferometric laser imaging for droplet sizing, or ILIDS. So ILIDS is a planar measurement technique for droplet sizing. So we have seen that LDV is a point measurement technique, but PIV is a planar technique for measuring velocity. So analogous to that, we have PDPA, which is a point measurement technique for measuring particle size, and ILIDS is a planar technique for measuring particle size. So this is analogous. However, the principle of application of ILIDS is very much different from PDPA, although both are based on collecting Mie scattering images from the particle. we can use eyelids for sizing bubbles and in general transparent spherical particles. So here two conditions are important. One is it has to be transparent, next it has to be spherical. Okay. So that is the reason why some people prefer using this term interferometric particle imaging, because here we can measure any type of particles, not only droplets, as long as they are transparent and spherical. So some people call it as interferometric particle imaging or IPI technique. And apart from particle size, it is also possible to measure particle velocity and as well as number density also in this technique. So let's see how this technique works, the principle of the technique. So this is shown here in this schematic. So here we have a spherical droplet which is illuminated by a laser sheet. Then part of the light is reflected, as you can see here, the red lines, and part is refracted. So this refracted light corresponds to first order refraction. We have discussed this already. So here we are considering P is equal to 0 and P is equal to 1. So 0th and first mode only, though there are other modes present also. So now here you see that this corresponds to two points here. Okay. This point corresponds to the point of reflection and this is point of refraction or first order refraction. And when you image this using a collecting lens and if you focus this image of the droplet, you actually see this. So each droplet is imaged as a set of glare points or pair of glare points. However, you see that here we are imaging at a particular angle. So this is also important in this technique. So what is happening here actually? So if you remember, these scattering intensity around a particle when it is illuminated by a light source. So in this region, so this region means this refers to forward scattering region. So if you remember again, so this is theta is equal to 0 and this corresponds to mainly it is dominated by diffraction, while this is called forward scattering and this part is called backward scattering. So we are in the forward scattering region. So what happens in this case, the light which is reflected and refracted, okay, they are interfering with each other. However, in the focused plane, we see these 2 points which are known as glare points. However, if we defocus, so if we deliberately defocus, all other techniques till now, whatever we had optical techniques we had discussed, those are all focused technique, means you always try to focus the image, but in this case you defocus. So when you defocus, then what happens? You get a fringe pattern like this. Why? Because the reflected and the refracted ray interfere to produce the fringe pattern. And that is the reason why the scatter plot around a particle, around a spherical particle, it shows oscillatory behavior. So if you see the scattering in this zone, which means in the forward scattering zone, you see this kind of oscillatory behavior, and actually that is because of interference due to the reflection and the refraction. But why they are interfering? They are interfering, and why they are interfering to produce fringe pattern? Because there is some path difference created, because this, as you can see here, the light which is being refracted, it travels a longer distance. So that is why there is a path difference, or this causes a phase difference also. And this is the reason why, and this is the condition for interference. Now, what is interesting here is that the number of fringes that you see, number of fringes means one pair of dark and white band constitutes one fringe. So, the number of fringes here is proportional to the particle size, and it can be shown using geometric optics. So, we can get basically a relation like this. So, here you see that the particle size depends on the wavelength of the light, the scattering angle, the refractive index, as well as the collecting angle. So, collecting angle is basically this angle, okay, which is dictated by this distance, how far your lens is from your imaging plane, and this width of the slit. So, this dictates the collecting angle. So, but for a given experiment, all these are constants. So, finally, you get a very simple relation, that is particle size is equal to number of fringes times the experimental constant. So, what we need to measure is basically the particle fringe number count. Okay. Now, what is fascinating about this technique is that it does not depend on the shape of the interferogram. So, whether this interferogram is circular or of any shape, it does not matter. What matters is only the number. And also, the particle size is not related to the size of the interferogram. Only the number count of the fringes matter. Okay. So, here droplet size is proportional to the number of fringes. So, this is the basic principle of this ILIDS technique. Now, in case of a spray, we have many droplets, or in any multiphase flows, we have several particles. So, you get several interferograms like this, as you can see here. So, this is a typical image acquired in a spray. Now, in here we need to process this kind of images to identify first of all where these fringe patterns are, and once you do that, you have to go and count the number of fringes in each fringe pattern or interferogram. However, this has to be automatically done through some image processing code. It is not possible to do this manually. So, now if you have dense sprays, or if the particle mass loading or volume fraction is high, then the interferograms interfere with each other, or they overlap with each other. For example, here in this case. So, in this case, processing the images or counting the number of fringes is very difficult. So, as the volume fraction goes up, then sometimes it also becomes impossible to identify the fringe patterns. So, the technique basically fails. So, the applicability of the technique is restricted to dilute, very dilute loading only. Now, this group from Japan, they came up with an excellent idea of solving this issue up to large extent. So, what they did is they put a pair of cylindrical lenses in the optical path, and they compressed, or I would say they optically compressed the interferograms to make them rectangular. Because as I said, the particle size does not depend on the shape and the size of the interferograms. So, they optically compressed each interferogram. So, now that improved the number density limit up to which the technique can be applied significantly. So, as you can see here, now we have rectangular fringe patterns, and now your image processing is also relatively easier. However, still the problem remains. So, even in this case, if the particle number density is too high. So in this case also the overlapping of the fringe pattern can occur. So mostly ILIDS technique is restricted to dilute to dense sprays. It should not be too dense with this approach. However, if you actually have dilute spray, then this technique can still be used. Okay, if this overlapping can be avoided, or you can take care of the overlapping somehow in your image processing. So this is how we get planar measurement of particle size. This means that now I can identify individual fringe patterns and I know the particle size. So at any instant of time, I can measure particle size in one plane. Okay. So that is the main advantage here. So the image processing in ILIDS is involved. I mean, you have to identify the fringe patterns first, and this is a typical fringe pattern. I would say that this is a very good fringe pattern. Sometimes because of noise due to various reasons, right? Background noise, electronics noise, or due to multiple scattering, if the number density is high, you may get a very noisy signal. So this is a typical signal from a fringe pattern. Then we do Fourier transform of that to calculate the fringe frequency instead of counting as such the peaks, which can be erroneous. We do Fourier transform to calculate the fringe frequency. Okay, and once you know the fringe frequency, you know the fringe count, and then you find the particle size. Now, similar to particle image velocimetry or particle tracking velocimetry, we can capture two ILIDS images at a very short time interval, and we can track individual particles in the two images to calculate now the particle velocity. So this is how we get particle velocity in addition to particle size. And we can also count the number of particles that we have identified in an image, and that can give an estimate of the number density. However, the validation ratio in this technique is typically low. Validation ratio means how many particles you actually identify in your image processing to how many particles which are actually present. Because we don't identify all particles and find its size even if it is present because of various image processing criteria. So, for example, if a fringe pattern has very low signal to noise ratio, we reject that. So because of this rejection, the validation ratio comes down. So the number density is usually underestimated. However, it gives, if you are interested in relative number density, so let's say compared to this location, what happens to number density at this location? If you want to know that, you can get that information from here. Okay, so the advantages of the ILIDS technique, as I said, is simultaneous planar measurement of droplet position, or I can say particle position, size, velocity, number density. All this we can get. And because of this ability, we can get several particle flow statistics which are otherwise not possible. For example, spatial correlation between particle velocity. So if we want to correlate particle velocity with itself, okay, that we can do. So this is similar to the 2-point statistics for turbulence that we have discussed. And moreover, we can find these statistics conditional on particle size, because now you know the size. So you can divide your particle size distribution to bins, and for each particle size class you can calculate this statistics. So that is a major advantage. But its uniqueness is that you can get this spatial correlation. in contrast to PDPA or PDA, which cannot provide this spatial correlation because that's a point measurement technique. Similarly, we can get relative velocity between droplets. We can characterize droplet clusters or particle clusters. We can calculate group number, and also we can calculate instantaneous short term in diameter or interdroplet or interparticle spacing. So at any instant, you can find what is the average characteristic size, particle size. Usually, we get the characteristic size by collecting large number of samples over a long period of time. That's how you get the characteristic particle size. But in this case, at any instant we can get that information. Okay, so that is the advantage. And also, as we will see, because this is also a planar technique, so for two-phase measurements, we can combine ILIDS with other planar technique, for example, PIV or LIF or planar laser induced fluorescence technique. And also, it is cost effective in the sense, if you already have a PIV system, then it is possible to modify the collecting optics and you do ILIDS. Okay. So, in that sense, it is cost effective. But there are limitations also. The measure limitation is the limitation due to number density. So, as I said, the number density up to which you can apply this technique is far below that of PDPA. Okay. Above certain number density, even the PDPA technique would fail. But that limit is far below for ILIDS compared to PDPA. And in this case, the measurement area is typically small, which is about 1 centimeter to 1 centimeter, which is a very small area. Because here we have to compromise between minimum particle size and the measurement area. So, the closer we go to the viewing area, the better it is in the sense of minimum particle size we can measure. But in that case, our viewing area becomes limited. And yeah, so as I said, all particles or droplets may not satisfy the image processing criteria, so the validation ratio is low. So now we will see how we can use ILIDS for two-phase measurements. That is, at the same time, if we want to measure now the carrier phase velocity, how we can do that? So that we can do by combining ILIDS with PIV, because both are planar techniques. So it is possible to combine. So in this case, what we'll do is that now let's say we are measuring a spray, and here we also want to measure the gas velocity around individual droplets. So in that case, what we can do is that we introduce some tracer particles. So here, for example, here you see you have some tracer particles around this droplet. And now we do the ILIDS as well as we do PIV by putting. So you know that for ILIDS, we must collect the light, the scattered light at a particular scattering angle, as you can see here. So now at the same angle only we should visualize the PIV. That is why we have put a beam splitter. Okay. So you can imagine this scattered light which is coming, it is divided into two parts. So one part goes to ILIDS camera, one part goes to PIV camera. So as I said, PIV is a focus technique. So in this case, you see this droplet as a pair of glare points. And also you see that around the glare points you have these tracer particles, because you have added tracer particles. On the other hand, in case of ILIDS, you see a set of fringe patterns for this droplet. Now, what will happen to these seeding particles in the ILIDS image? These seeding particles are basically solid particles. They are not transparent. So, in the eyelids image, they will be simply defocused. So, you won't see any fringe pattern here in the eyelids image. So, in the eyelids image, it is easier to identify the fringe patterns because this does not produce any fringe pattern. Only the droplet would produce the fringe pattern. So, now you process the eyelids image and you get particle size, particle velocity, or droplet size and droplet velocity in this case. Now, in the PIV image, we can remove the droplet because we know the position of the same droplet in the eyelids image. We can track it and remove that image so that here you have PIV image devoid of droplets. So, now you process this, okay, and you get the gas velocity. So, finally, you get both particle measurement as well as measurement of the gas flow. But this leads to some challenges which is known as center discrepancy. This is, I am not going too much detail into it. So, what happens is that when you image the same droplets as shown here, so here we are using a droplet generator. So, a droplet generator is a device which generates stream of same size droplets. So, you can say it is a simplified spray. Okay. So, why we use this? We use this to basically to establish a technique, first of all, to see how a technique would work before we go into the spray, which is much more complex. So, when we project the same droplets identified in both images in the object plane, a discrepancy occurs and this can be separated using some kind of calibration approach. So, as you can see, depending on the position of the droplet in the image, the center of the fringe pattern and the center of the glare points for the same droplet. So, you have the same droplet, you are imaging through two different cameras, but their centers do not coincide, as you can see here. So, here it lies on the left side, here they are nearly coinciding, here it is on the right side. So, this is called center discrepancy. Okay, this can be taken care through some kind of calibration approach. And this slide shows the image processing. So, as I said, you first process the eyelids image, then you process PIV image, you combine them, and finally you get flow field like this. So, you get particle size, you get particle velocity as shown in this, it's shown by the red circles and the blue arrows. You know the number density of the particles. Now, you also know the flow velocity or carrier phase flow velocity around the particles. So, you have now all this information with you, and this is at any instant of time, and you capture several images. So, you have so many realizations present which you can use to calculate vital statistics. So, this is an example of how the combined technique was used for two-phase flow measurements. So, here you have a spray and there is a co-flow around the spray, and this co-flow is seeded with tracer particles. Co-flow means here you have a air velocity, and this technique was used for two-phase measurements, simultaneous two-phase measurements at different locations in the spray. So, as I said, it gives you various two-phase statistics. So, that is what is the speciality about it. So, here is an example of the size distribution. So, as I said, you can consider different size class of the droplets and you get all the statistics for in each size class. And you know the Stokes number for each size class. For example, here you get Stokes number based on integral time scale of the flow or large eddy time scale, and you see that they are very good flow tracers. All the particles or all the droplets in this case are very good flow tracers as far as large scale eddies are concerned. However, that is not the case when you consider Kolmogorov scale. You can calculate Kolmogorov scale. Why? Because you have measured now the gas phase velocity also. Otherwise, you won't be able to do that. So that is the advantage. So here you see how the mean flow field look like in this case. So in this example, you have a kind of a vertical flow present at certain distance from the injector exit, and the flow is nearly homogeneous, isotropic, that also we can show, and then we can calculate this correlation between the particle and the carrier phase velocity. So that is the main advantage of this technique. So correlation means here you have the velocity of the particle, here you have the velocity of the gas at a given time instant, at a given separation distance. So you can calculate this correlation means you calculate these two velocities, you just multiply them and do this for all time instants and take an average. Now you can get this correlation as a function of particle size class as well as a function of the separation distance. Separation distance means the distance between the two measurements. So here, for example, what we want to know, if I have a particle here, how it influences the carrier phase, the gas phase, as we move away from the particle. And here we see that the correlation reduces as expected. So as you move away from a particle, its influence would reduce. Okay, but now what is interesting is that the quantification of this. So you see that as you move, let's say, from radius of separation from 1 to 8, the correlation still stays quite strong, from about 0.9 to about 0.7. Okay, so this means that the particle and the fluid velocities are strongly coupled. Okay, so if there is any fluctuations in the particle velocity, the fluid will also realize that, or the other way around. So, and also you see this, how the behavior is depending on the particle size class. So all size class don't behave similar way. For example, the correlation for 50 to 65 micron particles is less than 20 micron particle. The correlation between the particle and the gas phase reduces in this case if the particle size is larger. Okay, so this means that the particle size has, the larger particles has larger inertia. Okay, so they have higher Stokes number. So that is the reason why the correspondence between the two phases is lost for larger particles in this case. And we can calculate also particle to particle velocity correlation. So if there are two particles, how well are they correlated? So, and also because now we are characterizing the gas phase turbulence, we can also calculate the gas phase correlation. So there are three things: droplet correlation, droplet gas correlation, gas to gas correlation. So now all these three things are there, and also we measure both components. So here you see, for example, this represents the axial component, this represents the cross stream component, okay, and they behave differently. So the final point is we can get to understand lot of physics from these measurements. And yeah, this is one more example of how detailed analysis we can do. So in this case, the POD analysis of the gas flow has been done to capture the gas flow structures. POD means proper orthogonal decomposition analysis of the gas flow, so that we can capture the large scale features of the of the flow. Okay. So you can think of this as the following. So you know, according to Reynolds decomposition, this is mean plus fluctuations. But we know that in the when we say U dash, this itself contains spectrum of turbulent eddies. So out of those, the small scale eddies are homogeneous and they are isotropic basically. They have similar behavior. So that is why they are random in nature. However, the large scale eddies are anisotropic. Okay. So they represent the flow structures in your flow. So one way to visualize this is to further decompose this and say that this represents the large scale eddies and this is small scale eddies. Okay. And what we are doing here using POD is to capture this. The large scale eddies we can capture. Okay. And we can reconstruct the flow using only large scale eddies. So once we are able to do this decomposition, I can capture the flow field like this. Okay. And with this, I can study how the particles respond to these large scale features individually. So that is the beauty of this approach. Okay. I'm only giving an overview of this. You can go through this paper if you wish to understand more. Yeah. So we can calculate basically the particle or droplet gas correlations for each of these structures or coherent structures or large scale eddies separately. Next, ILIDS also facilitates measurement of particle clusters. Okay. I will talk about this later when we discuss measurement of particle clusters. So this is this radial distribution function. Basically, you can say it provides a statistical measure to quantify the length scale of particle clusters. Okay. So closer to a particle, this radial distribution function is higher. As you move away from a particle, this radial distribution function would reduce. So the place where it becomes 1, it provides a statistical measure. That separation distance provides a statistical measure of the particle clusters. So now the point here is that using ILIDS, we can do this conditional on particle size such that we can know particles of a given size, how it clusters, what is the length scale of such clusters as shown here. For example, here this shows that the length scale of the clusters increases if you consider particles of larger size in this example. Okay. Yeah, so here qualitatively you can see a particle cluster and its length scale. And finally, if you remember in the two fluid model, we had different source terms in the turbulent kinetic energy equation. So the turbulent kinetic energy equation for a two-phase flow, a particle-laden flow, is equal to, I hope you remember this, we had discussed this. So this is the two-phase flow, turbulent kinetic energy, rate of change of turbulent kinetic energy in two-phase flows. This is equal to rate of change of turbulent kinetic energy in single phase flow plus some source terms that contains the correlation between particle and the fluid phase. And here we get actually 3 source terms. Okay. Now, this term we have discussed it earlier quite a lot while I talked about turbulence modulation. So whether turbulence would increase or decrease in this model, it is according to the computation between this term and this term. So if this term or the particle gas correlation is higher than the correlation of gas with itself, then turbulence would be enhanced as per this model. So this term we know that is always important as far as turbulence modulation is concerned. But the question is, these terms where we have correlation between fluctuations of particle number density and particle velocity and gas phase velocity, can they be important? Now, these kind of measurements, what I just spoke about, that is application, that is through application of ILIDS PIV technique, facilitates evaluation of such quantities, and that is what was done here. So you can see that the first term is always dominant. However, the second and third term can also be important. And when that is important? When you have particle clustering. So if particle clustering in a flow is occurring, then you can expect correlation between local concentration of particles and the particle velocity itself. Okay. This is because when particles tend to cluster, locally their velocity changes. Okay. It is difficult to say whether it increases or decreases always. It is not universal, but definitely it changes. And that influences turbulence modulation. And that was shown here basically. Okay. So again, to briefly give you an overview of another application of the ILIDS technique, where it was combined with planar laser induced fluorescence technique. So till now we considered measurement of the carrier phase. When we said measurement of carrier phase, we only focused on measurement of carrier phase velocity. But it is in many applications we may have to measure other properties of the carrier phase. For example, carrier phase temperature or carrier phase composition. For instance, in case of an evaporating spray, for let's say you have a fuel spray, you inject a fuel spray, the droplets evaporate. And now how the carrier phase composition changes? Why should it change? Because you are adding vapor to the surrounding phase, to air, let's say, in combustion applications. So now you have a mixture of air and the fuel vapor. And this mixture or the composition is very important as far as combustion process is concerned, starting from ignition to the flame propagation, to energy release, to pollutant formation. All this depend on how well the two, the air and the fuel vapor are mixed. So that is why we need to measure the concentration of the vapor phase or the mole fraction of the, or mass fraction of the vapor phase. So if you know the mass fraction of the vapor, then you know the mass fraction of the air also. Okay. But in case of multi-phase flows, like in sprays, it is complex because the concentration of vapor at any location, it depends on the particle phase itself. Now, which properties of the particle phase? It depends on particle size, it depends on particle velocity, it depends on particle concentration. Okay. So all these are important, and this is the reason why we need to measure the particle properties, size, velocity, number density, as well as the vapor concentration around the particles. Okay. So how do we do that? So that can be achieved by combining ILIDS and lift technique. So I will discuss this in the next class.